Hey, Algebra 2 friends, here we are looking at trigonometry. We're going to be finishing up the year with trigonometry in chapters 13 and 14. So let's get started. We're going to focus right now on section 13.1, where we're going to deal with right triangle trigonometry. Now, my true hope, friends, is that we have spoken about trigonometry in geometry class, and so some of this will be review, but some of it will be new. If you remember, the study of trigonometry focuses on angles in their relation to the sides of a right triangle. So, for instance, let's say I'm dealing with the following right triangle, and I know that this is the hypotenuse, right? And this, if we're standing at this angle, and this little symbol is called theta, and that's just a Greek letter that we often use for angles in mathematics. So if I'm standing here at this angle theta, the side over here would be considered the opposite side. And then the side right here would be considered the adjacent side, okay? And so what trigonometry gives us is relationships based on angles specific to specific angles. So we have what we're going to talk about, trigonometric functions, okay? And those trigonometric functions, there are 6 of them that we're going to talk about today. Now, in geometry, we have spoken about 3 of them. We talked about sine, cosine, and tangent, and we had this really nice mnemonic device that said so, ka, toa. And what this helped us remember is that when we're talking about the sine of an angle, let's say the sine of angle theta, the ratio that we would get when we consider whatever angle this is would be opposite over hypotenuse. And so that's why we have so, S-O-H, sine is opposite over hypotenuse. So if you don't know this, can you guess what cosine of theta would be? Hopefully you're seeing AH, that would be adjacent over hypotenuse. So I can find these different values based on a specific angle. Now, the funny thing is, you guys remember that when we're dealing with geometric figures, particularly angles in triangles, if I have 2 triangles with the same angles, those triangles are similar. So even if this were, say, a larger triangle, and I'm still dealing with a right triangle and the angle theta is here, then I know the third angle will be exactly the same size. And so I know definitely that I'm dealing with a similar triangle. Well, do you remember similar triangles, how the ratios of the sides were proportional? Well, this proportionality is what we're playing on when we discuss the trigonometric functions. So sine of theta, whether we're dealing with this triangle or this triangle, is still going to have the same ratio because it's going to be opposite over hypotenuse here, or even opposite over hypotenuse here, which is going to have the same ratio. You guys with me? If this is not making sense and you're like, lady, I do not know what you're talking about, please, oh, please, oh, please, talk to me at some time personally so we can get this straightened out, okay? If you haven't been in my geometry class and you haven't seen it, let's talk about it. All right, so tangent of theta is opposite over adjacent, all right? And so that's what the TOA stands for. So once you've got those 3, they are tied to, or they are related to, these other 3. In fact, these other 3 trigonometric relationships or functions are really just reciprocal relationships. So what am I talking about? Well, the cosecant is related to the sine function, so we would write it as CSC. That's the abbreviation for cosecant. So cosecant of theta would be the hypotenuse over the opposite side. So it really is just flipping, or the inverse of the sine. Cosine is going to be the reciprocal of the secant function. So we would write secant function is secant, SEC, theta. And so since cosine is adjacent over hypotenuse, secant is going to be hypotenuse over adjacent. And I think it's pretty straightforward to see what's happening with this last one. The cotangent is the reciprocal of the tangent. Therefore, cotangent of theta, and COT is how we abbreviate that, it would be the adjacent over the opposite. I know if this is new for you guys totally, it's going to take a little bit of time for this to sink in. So take your time, get flashcards, make sure this makes sense to you before you move on. Let's talk about this next phrase. In this next section, we are asked to solve a triangle. What that means is given any old triangle, A, B, C, and of course we refer to the opposite sides as the lowercase letter. So the opposite of angle A is side A, opposite of angle B is side B. We use a lowercase letter, and opposite of angle C is side C. When you solve a triangle, you want to solve all of this information. You want to give me all of the side lengths, and you want to give me all of the measures of each of the angles of the triangle. So that's what it means to solve a triangle. And finally, when we talk about angles of elevation, this is something we talked about before in geometry. If I am like standing here and I am tilting my vision up to see the top of a building, I don't know what kind of building this is that has this kind of a siding, but if I look up and I'm looking up at the building, the angle of elevation would be the angle I make with my head in comparison to the angle, and in comparison to like a line parallel to the ground. Does that kind of make sense? I hope that doesn't sound crazy. And the angle of depression would be if I'm kind of standing up on top of a building and I am looking down. So this is the straightaway. The downward angle of my vision would be the angle of depression. So this is the angle of depression. And the other one is the angle of elevation. All right. So hopefully this was helpful. We should hopefully see a little bit more clarity, I hope, as we use some of these concepts. Let's go on. Here's just a reiteration of what we just talked about in terms of the trigonometric functions. But what I want you to see also is this nice relationship with the fact that sine and cosecant are reciprocals of one another. That means that cosecant is 1 over sine of theta. And similarly, the reciprocal relationship between cosine and secant means that secant theta is really 1 over cosine theta, and cotangent celebrates that relationship with tangent theta as well. All right, so let's go ahead and take a look at this next example. Find the trigonometric values. Find the values of the 6 trigonometric functions for angle theta. All right, let's go ahead and write those relationships down real quick. Though I didn't write down all of the relationships, I wrote my little mnemonic device, SOHCAHTOA, so I can go ahead and work this out. So we are going to stand here at angle theta, and we are going to use this triangle that we already have a lot of information about to find these relationships. So if I'm standing here, this is supposed to be me standing here. It looks crazy. If I'm standing here opposite over hypotenuse, which is sine, it's going to be 4 over 5. And right now, since I know that the reciprocal of sine is cosecant, I'm going to write 5 over 4. Next, I'm going to do the cosine of that angle. And the cosine of that angle is going to be adjacent over hypotenuse. And so I'm looking for the adjacent side over the hypotenuse. So that's going to be 3 over 5. And again, we know that there's a reciprocal relationship here with secant. So I'm going to do 5 over 3. Finally, I need to figure out the tangent, and then I'm going to get the cotangent as a result. So tangent we know is TOA, opposite over adjacent. So that's going to be opposite over adjacent here, which is going to be 4/3. And we get 3/4 as the cotangent value. In example 2, we are given that we have the cosine value of an angle is 2 over 5. Find the value of the tangent of A. Well, I'm going to draw a quick diagram, and let this be angle A. And if the cosine value is 2 over 5, I know that cosine is adjacent over hypotenuse. Are you guys with me? So I have 2 and 5 here. To find the tangent, remember SOHCAHTOA, remember tangent requires us to know what the opposite and the adjacent is. We already have the adjacent, which is 2, but we need the opposite. How can we do that? Hopefully you're thinking Pythagorean theorem. So I already put it down, a squared plus b squared equals c squared. I'm going to use 2 as a, b as this side here, and the hypotenuse we have. So I've got 4 plus b squared equals 25, which leads me to subtracting 4 on both sides. I get that b squared is equal to 21. So b is equal to the square root of 21. That's what b is. So now what were we trying to find out again? The tangent of a. Tangent is opposite over adjacent. Sorry about that. Tangent of A has to be equal to opposite. That's the square root of 21 over 2. And so we get that our answer is C. Sometimes I don't like to show a lot of information at one time because when I look at a chart like this, I find it kind of overwhelming. So there's a part of me that wants to erase half of this and just discuss it, but this chart is going to be valuable. So let's discuss it kind of slowly, all right? Okay, so I blanked out all of that stuff so we can focus a little bit on just this business here. You guys remember this 30, 60, 90 right triangle and the 45, 45 right triangle? Let's start with this one first. 45, 45 right triangle reiterates the idea that if we have an isosceles right triangle, we know that the base, no, not that. We know that the base angles will be congruent. So we understand that this 45 and 45 is going to be the same. And so if the legs of the triangle are x and x, the hypotenuse will be x root 2. And we can get that by taking x squared plus x squared. That's me applying the Pythagorean theorem, getting 2x squared equals to c squared, and therefore c is equal to the square root of 2x squared, which is really just x root 2. I know that was fast. If you're like, man, I need to see that again, let's talk about it. Or you can go back to a geometry video, but no, let's talk about it, probably better. But we have this relationship here. Let's remember the 30, 60, 90 triangle situation. So if we had a 30, 60, 90 triangle, we started off when we thought about it by adding the opposite side, right? So that we have like this triangle. And after really considering it, if I added the same triangle on the other side, I'd have a equilateral triangle, right? All of these angles would be the same. This would be 60, this one, and this one. And therefore, it makes sense that if this is x, this whole side is 2x. So we found this whole relationship where we realized that the small side, the side opposite 30 degrees, whatever that value would be, the longest side, the side opposite the right angle, would be double. But then we had to figure this guy out. We did a little Pythagorean theorem again. X squared plus b squared, I'm calling this missing side b squared, was equal to 2x quantity squared. And with a little bit of work, we got that b squared was equal to 4x squared minus x squared, which means that b squared was equal to 3x squared, which means that b was equal to the square root of 3x squared. And you got it, b is equal to x times the square root of 3. And hence we get this. I know you're like, okay, what's the whole point of that? The whole point of that is that we now have information about very specific angles. Particularly, we can find the trigonometric relationship of, or the trigonometric values of each of these functions, of each of these angles rather, 30, 45, and 60 because of these triangles. So if we were to look for, let's say, the sine of theta, and theta being 30 degrees, I would stand here at my 30-degree angle, and I would say, oh, wait a minute, sine is opposite over hypotenuse. Are you guys with me? And that would be x over 2x, which is really just 1/2. And that's why the sine of 30 degrees is 1/2. So if I continue along with that process, what I'm going to see is that I'm going to get all of these really cool values. I hate to say it, but I'm going to have to pick up in another video. All right. I will see you guys soon and we'll finish talking about this chart.